Okay, hopefully you can see my screen.
I can.
Okay.
Let me go ahead and introduce you here. So this is project ART 17, Learning Enhanced Autonomous Navigation for GPS Denied Vehicles. And so the professor on this is Dr. Brendan Englot from Stevens. He's an associate professor in mechanical engineering at Stevens with interests in perception, planning, optimization, and control that enables mobile robots to achieve robust autonomy in complex physical environments. So specifically, he's looking at improving the reliability of autonomous navigation for unmanned underwater, ground, and area vehicles in noise-corrupted and environments with drifting sensors, incomplete knowledge of the environment, et cetera. So with that, Brendan, I'll turn it over to you.
Thank you. And that introduction of my overall research activity at Stevens also is highly relevant to this particular project, which is about a year underway. We're working with the DevCom Armament Center on problems of interest in GPS denied navigation for autonomous vehicles. And this is an overview of the goals of our project. We would like to develop a multi-robot localization and mapping framework that permits a team of unmanned ground vehicles, which I'll be referring to throughout the talk as UGVs, to build more accurate and comprehensive LiDAR-based maps in GPS denied environments. And that requires the regular exchange of information. And much of the talk will deal with how we do that efficiently. We also want these robots to use that information to make decisions. And so another goal is to implement autonomous multi-robot exploration of previously unmapped or unexplored environments, where the UGVs will leverage their localization and mapping capability to build a complete map of an unknown environment within a set of specified boundaries. And then finally, the traditional approaches to those above two problems often face challenges in terms of their computational complexity and their scalability when we use traditional optimization-based approaches for solving them. And so another goal of our project is to integrate machine learning tools into those capabilities so that we can hopefully learn in the settings of interest, learn the characteristics of those settings that will allow us to solve these problems approximately, but much faster for real-time applications and improved scalability. I should also note before I move ahead that shown here is the key platform of interest that we're using for the proof of concept solutions being developed in this project. It's a small electric research robot made by a company called ClearPath Robotics, and it's called the Jackal. It's just a very widely used customizable research robot, and it's very easy to swap the sensor payloads and put custom arrangements of sensor payloads on board. So we have 3 of these in our lab right now that we're working with for this project. So before I talk about multi-robot localization and mapping, I just wanted to give you a sense of coming into this project, what we were able to do with a single robot. So this is one example on the left showing a single robot's ability to travel through an unknown environment and use its LiDAR observations to build highly accurate maps and achieve highly accurate trajectory estimates without GPS, all just done using LiDAR and inertial sensing. And then on the right, another example of us doing that in an underground facility where we truly are GPS denied. This was in the Strataspace mine in Louisville, Kentucky, where the LiDAR is really one of the only beneficial sources of navigation information for the robot. And as it travels and observes places where there's overlap with previous measurements, it's able to make corrections to its map. So our goal is to be able to do that kind of thing more efficiently with a team of robots in a distributed manner that is also communication efficient. So this is the architecture for the multi-robot localization and mapping solution we have developed through our efforts in this project. And one of the key defining features of this architecture is that it leverages a very data efficient descriptor for sending LiDAR information between robots. Rather than sending full dense 3D LiDAR point clouds, we instead take that LiDAR information and we compress it down into a much more data efficient descriptor called scan context, which is shown at the bottom of this slide. And scan context allows us basically to provide a a low resolution version of the essential contents of the LiDAR scan that can be shared very easily over wireless communication channel with a team of robots and does not come close to taking up all the available bandwidth. Robots can decide if they would then like to request the full dense LiDAR information if they see scan context images that are promising and represent a potential match. And so using that approach, we've been able to develop accurate, coordinated multi-robot localization and mapping solutions. This is an example of a data set that we have gathered and used for testing and validation of our framework, where 3 different robots travel overlapping routes in a park, and they're using only their LiDAR and inertial data for localization. So one robot travels this pink figure 8, one robot travels this cyan figure 8, and this other one travels this orange figure 8. And there are only a few segments of those paths that are overlapping. If the robots did this in isolation, just on their own, some of these paths would build up significant error, especially the pink one, because the pink one travels through kind of an open field where there is not much useful information to support localization. So by the time the pink robot travels to this rendezvous location here in the center, it's actually built up quite a lot of error. And it's only through the exchange of information with other robots on the team that it's able to reduce that error and build a more accurate trajectory estimate. We have also used the Stevens campus as a proving ground for this framework, and we have developed and tested multi-robot data sets using our campus and different trajectories taken through our campus. So this is just an example of our framework on the right, managing to, by exchanging key messages and identifying useful measurement constraints between robots, build a highly accurate solution. Whereas a competing solution, which kind of represents the state of the art, this one ends up building up errors that can't quite be resolved just through the exchange of messages between robots. So even though some information is being sent to the pink robot by the yellow robot, there are still some errors that persist, and the robot's unable to make corrections to some pretty severe drift and error that find its way into the trajectory estimate. One key item worth highlighting associated with our proposed framework is its data efficiency. So the key, the 2 data sets that I just showed you, the one on the Stevens campus and the one in the outdoor park with 3 different robots, we keep track of the data overhead associated with all the communications required between robots. And most importantly, we look at the number of messages that are sent in order for these robots to develop these accurate navigation solutions. One key thing worth noting here is that the vast majority of messages sent are these data efficient descriptors, the scan context features. This accounts for the vast majority of the traffic on the network, very data efficient messages that are just providing low resolution descriptions of the LiDAR scans. And the more data intensive products that need to be exchanged, you can see these are being exchanged much less frequently and only when necessary. So our hope is that all of that can kind of provide the foundation for intelligent decision making, in addition to mapping and localization. And so we have also developed algorithms that allow a robot to explore an unknown environment and do so in a way, the goal of which is to produce an accurate map. And in order to produce an accurate map for a GPS denied vehicle, we need to be able to make predictions about localization uncertainty. So in addition to having a localization process that runs smoothly, we also need to be able to kind of forward simulate that process into the future, make predictions about the measurements that the robots will collect at future times, and then factor that into our planning process. So just to kind of give a snapshot of what that looks like when it's in progress, here's an example of one of our Jackal unmanned ground vehicles exploring an indoor environment and building a map. And you can see these blue candidate paths that it's considering. Along each of those candidate paths, the robot tries to forward simulate its measurement process, make predictions about the future measurements it will collect, and predict in turn how that will affect its localization uncertainty when it gets to the goal state, and the accuracy of the resulting map. So we take advantage of a few different cost maps that we blend together in order to do that. In addition to just the distance or time associated with each candidate path, we also generate cost maps for localization So in this case, blue represents lower cost, higher quality solutions. And in this case, the paths that are favorable for localizations are the ones that hug the boundaries of the obstacles. So the closer we are to the obstacles, the better that is for localization. This is another cost map capturing the value of this information toward exploring. And in this case, we want the robot to venture out into areas it hasn't seen before and expand the contents of its map and collect new information. And in this case, the most desirable areas to go are outside the boundaries of the areas that have been mapped. And so taking these different cost maps and blending them together into a single planner has allowed us to achieve high quality solutions that explore efficiently and also manage the accuracy of the map. So here's an example of some of the results of our framework. Oops, that does that. Let me play this video. This just shows a few simulation results, as well as one result from a real laboratory experiment. So this is just a simulation, and in showing this also, this comprises an important component of our research, is having a high fidelity simulation that we can rely on to capture the motion, the sensing of our robot, the robot's interactions with the environment, the geometry of the environment, and also especially the properties of the LiDAR sensor, that those are captured accurately in this simulation. So we've used this as a kind of proving ground to fine tune these algorithms and ensure that they're exploring efficiently and they're building accurate maps. And in this case, the robot is using the same localization mapping process I've described earlier to support its trajectory estimate. So it does not have ground truth information about its position. It is GPS denied, and it's only using these short-range LiDAR observations in order to localize itself. But you can see that it's making decisions that lead to fairly efficient exploration of an unknown environment and also a fairly accurate map. And then finally, this is a real experiment. So our goal was to be able to kind of develop in simulation and then port the same algorithms right onto hardware and have no loss of continuity. And you can see here the same algorithms work well on our hardware, where here we have our real Jackal robot exploring a laboratory environment at Stevens. Actually, this is the lab pictured right behind me in my virtual background here. The robot explored the entirety of this lab, navigated itself around the obstacles, and it did so fairly efficiently. So I'm now going to switch gears and talk a little bit about the integration of machine learning into these algorithms to allow them to run more scalably and more efficiently. Before I do that, I should note that although we showed you some results we have thus far for true multi-robot distributed localization and mapping compatible with Wi-Fi communication constraints, we do not yet have multi-robot exploration working. That is still a work in progress. So at the end of the talk, I'll discuss some of our ongoing work and our goals in that area. But the remaining results you'll see will be for a single robot. And we hope that we can take these results combined with our multi-robot localization and mapping capability. And hopefully soon, within the next few months of our project, we will have fully functional multi-robot exploration as well that leverages similar algorithms. One of the challenges of trying to solve this problem over large scale environments with high resolution maps is that these algorithms depend on forward simulating the robot's measurements and localization process. And unfortunately, that's very computationally expensive and it doesn't scale well. So we have wondered if we could train machine learning algorithms to essentially learn how to do what we call belief propagation. This idea of taking a robot's localization uncertainty, simulating its measurements and its actions forward in time, and then making predictions about what the localization uncertainty will look like in the future. So can we train a neural network to perform accurate belief propagation? That's one of the key questions that we're trying to answer in this project. And in addition, one of the other key questions is there a compact abstraction that could be helpful for capturing many different environments and kind of distilling them down to the essential representation that could perhaps be used across domains with different robots, maybe different sensors? And so our hypothesis in pursuing this research was that we could use graph representations and in turn graph neural networks to achieve that. And so what we've tried to do here is take all of the information about the robot's mobility, sensing capabilities, the measurement constraints relating all of its past measurements, and potential waypoints where it may wish to travel in the future, boil all of that down into a single unified graph representation that we have called the exploration graph. And so that's what you see here. This is an example of what an exploration graph might look like for a robot exploring an unknown environment. Our hope is that this can be the vehicle through which we teach a robot how to perform belief propagation and make good decisions over belief propagation with a nice compact abstraction that is compatible with deep learning. Okay, and so, you know, we're hoping also to do this not just in a deep learning setting, but in a deep reinforcement learning setting, in which our robot will learn optimal or near optimal policies for exploring that that contain all of the difficulties of belief propagation, making decisions over the outcomes of belief propagation in a manner that is kind of self-taught based on appropriately designed reward functions. So we would really like to be able to learn these policies without human intervention. We would also like to learn policies that are non-myopic, and they apply well across a wide range of different test environments. And hopefully, one of the key things we're looking to achieve is scalability as well. And so just to clarify from the different elements of this graph that I showed you a couple of slides ago, what is being achieved with which components of the graph as a whole comprises our representation of the state. So the state of the world in which the robot is learning is represented by this graph showing all of its past, what we call its pose history. So the position and orientation of the robot at every time that it collected a measurement. So in addition to the robot's pose history, we keep track of the robot's current pose, landmarks in the environment that have been useful for navigation, and also these are denoted F for frontiers. These are waypoints that we place at the boundaries or at the frontiers of the map, which represent where the robot may wish to travel next to continue mapping and exploring. And so our action space is a subset of that state representation. Our action space is just comprised of the different waypoints the robot may choose to travel to next. Okay, so what you see here is a much more simplified simulation than the one I showed you in the previous video clip. We wanted to start with something simple, make sure that we were learning policies that were robust, we're achieving highly accurate maps and doing it efficiently. And then eventually we wanted to scale this up in complexity. So this is a kind of a simple simulation where the robot's exploring an environment that has no obstacles. All it's using to map the environment and localize itself are measurements of landmarks. So all of the landmarks are shown by these plus signs. So gradually the robot will explore and discover where all the landmarks are hiding, and they're all mapped in purple, or excuse me, they are mapped in which color? In yellow once they are discovered. These yellow plus signs end up being coded into the map as obstacles, just so that the robot can keep track of them. And as the robot is exploring, it's considering all of the candidate waypoints available that are shown in purple, and the choice that it makes is shown in red. So what you see here are a few different deep reinforcement learning frameworks with different graph neural network representations compared against a few classical algorithms. So our deep learning solutions are shown on the bottom, and at top, what we have is a random algorithm that is just making choices purely at random, and you can see the effect that that has on the efficiency of exploration. A classic algorithm that simply travels to the nearest frontier. So this is an algorithm that will explore the environment very efficiently, but in doing so, it will build up lots of error because it is not keeping in mind the localization of the robot, not paying attention to its trajectory estimate. So lots of errors build up quickly. And then at the upper left, this is the algorithm that we have developed at Stevens that I showed you in the previous video clip, but is the one that we know is not scalable to large problem instances, and it's not scalable to high resolution. So we would use this upper left algorithm every time if we could, but we know that it has limitations in terms of its scalability. So our goal here is really to show that the deep learning frameworks at bottom are on par with the framework shown at the upper left. And another key issue that we wanted to investigate through this study was the issue of scalability. So the framework that we felt was providing us the best performance that was reflective of the optimal algorithm was this architecture shown in the middle. And choosing this winning architecture, we then wanted to see what are the limits in terms of how this policy learned here could be transferred to larger maps with different arrangements of landmarks. And so that's what you see here is us taking the winning architecture and applying it to a variety of maps of different sizes and seeing how well the policy works in environments that differ somewhat from the environment in which it was trained. And of course, every time we test this algorithm, there is a different randomized arrangement of landmarks that differ from what the robot saw during its training as well. But ultimately, we end up with, although there are some diminishing returns, and there only is a certain limit to which you can scale this map and still get the same performance, we did find a pretty good robust scalability of this to larger maps, where the performance of this policy worked quite well in terms of exploring these environments efficiently and building accurate maps that maintain the localization uncertainty at relatively low levels. So having proved to ourselves that that architecture was a way forward, that we were hoping would scale to larger problems, higher resolution maps, higher dimensional mapping scenarios, we then wanted to test it on our real UGV with real 3D LiDAR data and obstacle avoidance of three-dimensional obstacles. So the next question that we asked was, can we do this in such a way where the training is even more minimal than in the previous study? Can we train perhaps in just a single environment? In fact, this is the one we used in this next study, the one shown here with the office type environment that has a few desks scattered around a room enclosed by a wall. This is the environment that we used for training a system that was then deployed into a much wider diversity of environments. And this is done through what is called zero-shot reinforcement learning or zero-shot transfer, where the entire policy is learned only in this one setting and then immediately transferred to other settings that have not been seen before. We wanted to see if we could achieve that with environments of different sizes that contain different objects. And also, the most important question that we hope to answer was, if this policy was learned purely in a simulation, could we transfer it effectively to a real robot, deploy that real robot in a physical environment, and still have successful mapping and exploration outcomes? So once again, we were able to leverage our exploration graph paradigm to do that. In this case, looking at mapping scenarios that run on a real robot equipped with a real 3D volumetric scanning LiDAR, we had slightly more complex graphs that we were dealing with and a few different types of constraints on those graphs that had to be represented in our graph neural network. So this is the full set of measurement constraints that we need to consider for this type of mapping scenario. Odometry factors that link consecutive poses together. Sequential scan matching factors where LiDAR scan matching is being performed from one pose to another across consecutive robot measurements. And then also segment matching and pose matching that occurs with the aid of the LiDAR across non-consecutive poses. So these magenta and red links represent the robot traveling, revisiting a location that it saw before, and then establishing overlap between two non-adjacent observations. Those end up being the most useful constraints that eliminate the buildup of error that occurs over time. So we adapted all of this into an exploration graph that was suitable for learning with a deep reinforcement learning framework and a graph neural network. We incorporated waypoints once again into the graph representation. So the robot had the option of going back and revisiting locations it had traveled in the past, and also traveling toward the frontiers of its map. And so this is what the actual deployment of this on a real robot looked like, or actually the deployment in both the simulator and on the real robot used the same representation, the same data products, and have a very similar appearance. We keep track of the robot's current pose and we approximate its uncertainty. We look at the different motion planning options and frontiers that are accessible to the robot by planning through this map that is populated with obstacles. And then the map itself, we try to keep track of our confidence in how accurate it is as well. And that's reflected by the color scaling that you see here. So areas of the map shown in blue, we have high confidence in their accuracy, and areas that are in red, we have lower confidence. And so this is actually how the exploration graph maps onto these real data products. As the robot travels through this environment and it explores it and builds its map, its individual poses shown in green here all get added to our exploration graph. The frontier waypoints at the boundaries of the map where the robot is considering to travel next, those are all shown in orange here. And the constraints that are linking these are shown in red. These are all real constraints that are then fed as input as the state representation of this system to our graph neural network. And the neural network's decision-making is done over this abstraction of the robot's uncertainty and data and various localization and mapping data products. So this culminated with a real physical experiment, once again trying to explore the entirety of the lab in our ABS Engineering Center. So again, the same lab space pictured behind me here. We initialized the robot from different random locations in this lab space and tried to benchmark the accuracy and efficiency of how well it explored using this learned policy. And thinking back to the result that you saw in that video clip, the robot is now exploring that same environment and producing a comparable result that explores this environment efficiently and builds a fairly accurate map. Although this has been done now using a policy that was learned completely in a simulator. So it may be actually worth going back just to compare qualitatively this resulting map that you see here at bottom right and the result from the video from our original algorithm that did not use any machine learning. So originally, we just had an optimization-based approach, and I'll remind you what that final result looked like. There's a good representation of it. So we basically wanted to achieve the equivalent of this, except without having to do the costly optimization behind belief propagation and trying to choose the best path from all of the beliefs that had been propagated across the candidate paths. So instead, all of the decision-making entailed in this process is now just being executed by a reinforcement learning policy learned with a graph neural network. And so all of that optimization is instead being achieved simply by querying this graph neural network. So in terms of the next steps, we did see some limitations here in that there are some environments that are served better by some algorithms more so than others. And although we built a rather sophisticated algorithm for managing localization uncertainty, what we noticed is that there are some environments that actually a robot can explore them more accurately and more efficiently using simpler algorithms and more classical ones, like simply driving to the nearest frontier. So this is a particular environment we discovered, by testing out different environmental characteristics in our simulator. This environment tends to be explored more accurately and efficiently using a simple frontier-based approach. And so we wondered, can we train our graph neural network using a portfolio of algorithms where it learns not just from one algorithm, but it kind of learns from the best classical algorithm suited to a particular task? So if you're in an environment where algorithm A is the best classical approach, train using that one. Then when you're exposed to an environment where algorithm B is the best approach, train using that one instead. And so training using a portfolio of algorithms might allow us to capture the aspects of the best decision-making approach in environments with different characteristics. And in fact, we found that that was successful and allowed us to explore environments like this one more efficiently and accurately than with our original approach. So approaching the end of the talk here, I just wanted to note what our next steps are at present. We are really interested, as I mentioned, in applying this to a multi-robot team. We would like to take advantage of the coordinated, distributed localization and mapping capability that I discussed in the first few slides. And we would like to use that as the basis for autonomous exploration, where a multi-robot team could perhaps go back into that mine environment I showed you on my first slide, explore, fan out through the mine exchange information efficiently, and make very good decisions as a team about how to rapidly explore an environment like that, where it is using graph neural networks as a proxy for all of the expensive belief propagation that's needed to make those decisions. So we're in the process of building an architecture that will allow us to learn with exploration graphs that are designed for multi-robot teams. And we're also looking at problems that are more general than simply exploring. We're looking at a class of problems called persistent monitoring, where rather than having to explore everything from scratch, we may just have a designated set of targets that the team needs to continually monitor and collect observations from. So we're trying to develop architectures that can handle exploration, can handle persistent monitoring, and they can do so with heterogeneous multi-robot teams. Ideally, we would like to be able to take teams of robots like this that have different and complementary sensing capabilities, perhaps aerial robots equipped with cameras, ground robots equipped with LiDAR. Each will have different complementary sensing and mobility capabilities, and trying to optimally leverage them to monitor targets in complex environments and explore unknown environments accurately and efficiently. So that's all the material that I wish to share with you today, providing an update on the first year of our project. There's certainly some exciting progress so far, and we're also very interested to see how effectively we can get all this to work on a multi-robot team. So I'd be happy to take any of your questions.
Great stuff. Can you tell us more about how the robot or the robot teams figure out where they are in Earth coordinates, what their position and their orientation is, or how they're initialized?
Sure. So I'll go back to one of the results we gathered in the field with a single robot, just to give you an idea. So what I would say is I think everything I've shown you here is compatible with georeferencing these results, although right now the results you see here are just initialized based on where the robot's experimental run is initialized. So, oops, let me play these videos again. There we go. So in this video, everything is being mapped relative to the starting point that you saw at the beginning of the trajectory. So that might, be initialized through a georeferenced position fix that we could use so that everything we map from that point onward is referenced to that point. That would be compatible with how simultaneous localization and mapping algorithms work, since there's a continual buildup of error throughout this process that we're just trying to manage and keep things down to the levels they were at the outset of the mission. Similarly, in this mine mapping exercise, we initialize the robot from the entrance to the mine. We would potentially be able to georeference the robot's location there. And when the robot travels underground into the mine, all of the mapping it does from this point onward can be referenced to that, that initial starting point. But that's generally how we've approached this so far. One of the problems with multi-robot systems is if you lack that information, one of the things that makes multi-robot localization so challenging is you might be looking at observations that overlap and not have a good idea of the frame of reference of the other robot. I guess the final point worth mentioning on that question is that all of this is compatible with GPS information if we have it. So the good news is that the kinds of factor graphs that we use to solve these optimization problems, we can also provide GPS information, and it can be incorporated into the solution.
Yeah, I guess what confused me was when you said you're starting with inertial knowledge. My question is, if you had enough time, could you establish your Earth position inertially?
That's a good question. Based on the kinds of inertial sensors I have access to, at least, I think that would be challenging. When I mentioned fusing with inertial sensing, I should have clarified that we have a relatively low-cost MEMS inertial measurement unit on board this vehicle. And the main purpose of that is just to kind of help us maintain continuity in the estimate between LiDAR scans. So our LiDAR is scanning at 10 Hertz. We obtain a new scan every 1/10 of a second. And for that 1/10 of a second between scans, we'd like to also maintain accurate track of what the robot's doing. So that's the primary role for us of the inertial measurement unit, is is to accurately estimate what the robot is doing between scans.
Great, thank you. Any other questions from the room? No. There was one online asking about how these maps were generated. If you could just maybe elaborate on that.
Yes, let me open up the Q&A and take a look. Are the cost maps generated, or how are the cost maps generated? That's a good question. So let me go to the slide where those were shown. Okay. So we have ways of quantifying the benefits of these different regions of the environments to localization. These are meant to just kind of represent, so we would not normally generate the entire cost map in the course of solving and applying the algorithm. It's actually just meant to kind of visualize for you, what these costs look like when they are computed over the entirety of the environment. We would only compute these costs over the candidate paths. So normally you would only have this information over the blue candidate paths that you see here. But the way that we generate it is we actually, to generate the localization costs, we propagate the robot's measurement process, simulated forward in time across this path, make predictions about the robot's measurement. Then we actually try to go through the process of registering those observations to previous ones, kind of a simulation of the robot's localization process. We use that to determine how valuable the measurements are. So that belief propagation is used to generate this type of information. Here we've just generated it exhaustively, so you can kind of see its value everywhere in the environment. And the exploration cost map is a little bit simpler. For that, we're just using Shannon entropy. So this grayscale map that you see here, for this, we're using an occupancy grid map. So this is actually just a very finely discretized rectangular grid. We assume that every one of the grid cells in that map is characterized by what we call an occupancy probability. So the probability that one of these map cells is occupied with an obstacle, or whether it's free. So basically, we try to make decisions that will eliminate the largest amount of Shannon entropy possible over this regular rectangular grid map in which every grid cell has a probability of occupancy. When that probability is 0.5, meaning we don't know, we know with equal uncertainty whether it's free space or occupied space, then that has maximum entropy. So areas like this that are completely unknown and unexplored will take on the most appealing cost in the exploration cost map. So that's what you see in this map, is basically just a reflection of the Shannon entropy of the grid map containing all of the obstacles observed so far. But once again, we don't generate that exhaustively. In the course of solving this problem, we only evaluate that information over the paths being considered. So that actually is kind of a glimpse into why this is such a computationally intensive process. And that was our inspiration for using graph neural networks to solve this problem, so that we could query them and get rapid solutions to this type of problem.
Great. Any other questions? No. Well, thank you so much, Brendan. We appreciate you taking the time.
Yep, it was a pleasure speaking with you. Thank you.